Hello everyone, welcome to part 2 of the Optimizing IO tutorial. My name is Ritu Arora. We've already covered the first 4 topics mentioned on the slide in part 1 of this tutorial, and today we will be covering Introduction to Parallel IO Patterns and Introduction to MPI IO. Let us begin with the Parallel IO patterns, and then we will progress towards MPI IO. One pattern that we typically observe in parallel programs involves all processes sending their data to the process designated as root, and then the root process writes the collected data to the file. Now, as the process of writing the data to a file from the root process is sequential, the I/O done with this pattern can limit the performance and scalability of many applications. Another I/O pattern involves each process writing to a separate file, and the diagram shown on the slide here demonstrates that. The advantage of this approach is that each process is working in parallel with other process, and hence there's a chance of getting performance improvement. However, the disadvantage is that this pattern may result in too many small files to manage. If there are several thousand processes that are associated with a single compute job and they're all involved in writing several thousand files simultaneously, then the metadata server of the Lustre file system can get stressed out while managing or coordinating the metadata associated with the files. We covered the topic of Lustre file system in part 1 of the tutorial, by the way. And as we discussed in the previous part of the tutorial, if the MDS gets stressed out, then depending upon the architecture of your file system, your entire file system and the HPC system could go down as well. Usually the desired I/O pattern is when we can have multiple parallel processes associated with the compute job that are participating in I/O to a common file. And this particular pattern is shown here on the slide. Now, this pattern improves performance and provides a single file for storage and transfer purposes. So those are the benefits. However, when we have multiple processes attempting to write to the same region of the file, locks are needed for serializing access. And when we use locks, that results in degradation of the application's performance. Now that we have seen the different patterns for doing file I/O and what the desired pattern is, we will learn about MPI I/O and how to use MPI to do the I/O as shown on the slide with the desired I/O pattern. In general, we can say that the process of reading and writing in parallel is like receiving and sending messages. Hence, an MPI-like machinery is a good setting for parallel I/O. MPI I/O featured in MPI II, which was released in 1997, and it interoperates with the file system to enhance I/O performance for distributed memory applications. One of the advantages of using MPI I/O for supporting parallel I/O in applications is that it reduces the dependency on additional external libraries and hence can help in developing self-contained MPI applications. Let us consider the scenario in which we are given n number of processes in a compute job, and each process participates in reading or writing a portion of a common file. Now, there are 3 ways of positioning where the read or write takes place for each process. We can use individual pointers, or we can calculate explicit byte offsets, or we can use the shared file pointers. Now let us define certain terms that are used here. A file pointer is an implicit offset maintained by MPI. Individual file pointers are file pointers that are local to each process that opened the file. A shared file pointer is a file pointer that is shared by the group of processes that opened the file. While we will not be covering shared file pointers in this tutorial, we will soon see examples and APIs that involve individual file pointers and explicit offsets. In general, when we do any read or write operation in a file, say for example in C programming language, we first need to open the file using an appropriate function like fopen. In the same way, when we are doing MPI I/O, we first need to open the file. Now, instead of using the regular file open command in C, we will need to call the MPI file open function. Now, let us take a look at the signature of the MPI file open function. This function takes 5 arguments. The first argument to MPI file open call is the communicator, and this indicates that a file is opened collectively by a group of processes that are associated with the communicator. The second argument is the file name, and the third argument in this call is the mode in which we need to open the file. Now, there are predefined modes for opening the file that we will need to select from. For example, we can use MPI underscore mode underscore RD only, which stands for read only mode. And then we can use options like MPI mode write only or MPI mode read and write when we want to do both reading and writing after opening a file. And we can also use the option which is MPI underscore mode underscore create. This option will create a file if it does not already exist. Please note that we can combine multiple options as flags for the file mode using the bitwise OR operator in C or addition in Fortran. The fourth argument to MPI file open is an MPI info object. We will revisit the use of MPI info object in later slides. And in the first few examples that I will show you, we can set this value to MPI info null, which is again predefined in the library. The fifth argument of MPI file open function is the file handle. This file handle can be subsequently used to access the file until the file is closed. Once we open the file, we can do the I/O, we can have different processes reading or writing to this file. And once we're done with this business, we should remember to close the file by calling MPI file close function. The MPI file open call defines an individual pointer for the process and a shared pointer for the communicator. Once the file is open, then we can continue with the reading and writing part. MPI provides multiple types of calls for reading and writing files in parallel. There are API calls available with blocking or non-blocking synchronization mechanisms, and we can make a choice between using collective or non-collective coordination patterns of these calls. And then, for example, if we want to read a file in blocking non-collective coordination manner, then we can either use MPI file read with MPI file seek or MPI file set view calls, or we can use MPI file readat. If we use MPI file readat, there is no pointer involved and it takes explicit byte offsets as arguments. Now let us look at a very simple example of using MPI file read call while using individual file pointers. Because we would be using individual file pointers, we have to use MPI file seek. And like I mentioned, we could also use MPI file set view call. We will take a look at the MPI file set view call shortly. And in this example, we are using MPI file seek. So this will set the individual file pointer for each process. And if you notice in this example, the first thing related to MPI file I/O we do is we declare the file handle using the MPI underscore file type. Then we pass this handle to the MPI file open call. And in here in the MPI file open call, we specify that the mode in which we want to open the file is the read only mode. And then we set the pointer with file seek, and we have the file read happening. And then once we are done with the reading, we close the file. In addition to the MPI calls for opening a file, reading a file, and closing the file, let's look at some of the other logic that this code has. It includes the line for calculating the buffer size, and this buffer size is basically calculated by dividing file size by the number of MPI processes that are participating in the computation. So we have here file size, which is defined as 80 or 80 bytes, and then size would be, if we use 4 processes to run the code, the size would be 4. And then we calculate the exact number of integers that we would be involving here. So we divide buff size with size of integer. And then we pass these values to the MPI file seek and the file read calls. On this slide, we see a slightly different version of the program we saw on the previous slides. Here, instead of using two MPI calls for doing the read operation, which is like instead of using MPI file seek and MPI file read, we're using a single call. We're using MPI file readat. The previous calls we saw, they used individual file pointers, and here in this example, we're using explicit byte offsets. Now let's look at what's going on in this code. So just like in the previous code, we define the file handle with fh, and then we open the file in the read-only mode. Name of the file is dfile, and then we call MPI file readat, which accepts the file handle, and it accepts the buffer, the number of integers that would be involved in the reading process, and the buffer in which we want to store the read values. So here the buffer that we want to use is defined as an integer buffer. We say int buff and in square brackets nins, which means we're declaring a buffer of length n ints. And this buffer is then passed to the MPI file readat call. And the offset here is rank multiplied by buffer size. So if our buffer size is, let's say, 40 and rank is 0, so basically the offset is 0. If our rank is 1 and buffer size is 40, our offset would be 40, and so forth. So here we demonstrate how we used explicit offsets to do the reading from a file. And then we store the value in a buffer called buff. And in this example, we are just printing the value of the buffer at the 0th element. And note that this call MPI file readat, it basically combines what seek and read achieves into separate calls in one step. And this is recommended for developing thread-safe applications. Just like we have a wide variety of MPI functions available for reading data from files, we have a similar range of functions available for writing data to files as well. When we open the file in the write mode, we have to remember to pass appropriate flags to the MPI file open call. The suggested flags, the recommended flags could be MPI mode write only or MPI mode read and write. And if the file does not already exist, you might want to create it first. And the flag to use for that is MPI mode create. Like I mentioned previously, we can combine multiple flags in the MPI file open call by using the OR operator. And note here that when we are wanting to open a file in blocking non-collective coordination manner, we can either use MPI file write with MPI file seek, or we can use MPI file write with MPI file set view. Both these combinations of MPI file write with file seek and file set view uses individual pointers. Now, if we want to use explicit byte offsets, we can call MPI file write at API. We will look at examples of using these calls shortly, and we will also take a deeper dive into how does MPI file set view functions. So this particular function will basically be used to describe the part of the file that is accessed by a single MPI process. This function basically changes the process's view of the data in the file. Now let us review some sample code for writing data to a file using MPI I/O calls. In this example that we have here, let's go line by line. So the first two lines here are for including the stdio.h file for the IO and then mpi.h for the MPI functionality. We have a call to int main, and then we have the declaration of the file handle named fhw on line number 5. And then we have MPI init call for initializing the MPI environment. We have calls to MPI rank and size. And then at line number 10, we declare a buffer of type integer and length n. And in the for loops that runs from line 11 to 13, in this for loop, we are initializing this buffer to the value of the variable I, which is the loop variable. And then at line number 15, we're calculating the offset values. We're calculating the location in a file at which each process should do the writing. So what we have here is the formula offset is equal to rank multiplied by n divided by size multiplied by size of int. We multiplied by size of int because basically offset is calculated in bytes, like I was mentioning. Rank represents the rank of individual process, and as we noticed in the 16, and if we have, let's say, 4 MPI processes participating in the computation, 16 divided by 4, we will get 4. So in this formula here, let's say we have rank 0 for the process with rank 0, the rank would be 0 and rest of the values don't matter and its offset is 0. And then for the process with rank 1, the offset would be 1 multiplied by 16 divided by 4, assuming there are 4 MPI processes participating in the computation. So this would be 4. So 1 multiplied by 4 multiplied by size of int. So let's say the size of integer or int on the platform we are working on is 4 bytes. So basically the offset calculated here for process with rank 1 would be 16 bytes. Likewise, the offset would be calculated for process with rank 2 and so forth. Next, at line number 16, we open the file and the name of the file is data file. We open it in the mode MPI write only, and we have the flag MPI mode create passed here as well, so that if the file does not already exist, it will be created first, and once it's created, it will be used for writing purposes. And the file handle that we're passing here is fhw that we created on the previous slide. And then on line number 17, we are just printing certain values, ranks and offsets to see if everything is getting computed correctly using the formula at line number 15. And then at line number 18, we have the call to MPI file write at. This is using explicit byte offsets that we calculated at line number 15. So for each process, we are telling MPI how many number of integers should be written. I say integers because the data type we pass here is MPI underscore int. You are welcome to use derived data types as well here, but here we are using primitive type MPI int as the data type. So we are saying that we are writing integers, then we pass the count of integers, we pass the offsets as in from where the writing should take place and such. And then we close the file, we call MPI finalize, and we return from this main function. Now let us look at how to use MPI file set views and take a deeper dive into it. So this function, like I mentioned before, changes the process's view of the data in the file. So file views are particularly useful when data has to be written non-contiguously to the disk. And on the slide here, we are revisiting the desired I/O pattern that we saw previously. So when we have processes that need to write to a shared file, we need to assign regions of the file to separate processes using, like I said, some mechanism. And here the mechanism is MPI file set view. If we take a look at the signature of this function, it accepts certain arguments such as the file handle, the offset or the displacement for each process to do the writing or reading from. And then we pass the MPI data type argument for elementary types or the E types. And then we pass the argument for the file type, the data representation, and the info object. It's important to understand each of these individually, as in each of these arguments individually, and we will go over these shortly. So the file views are specified using a triplet of displacement, E-type, and file type. Displacement represents the number of bytes to skip from the start of the file. E-type represents the unit of data access, and it can be any basic or derived data type. The file type specifies which portion of the file is visible to the MPI process. So here, as you see on the slide, we can use the combination of different E-types and gaps to construct our file type or the pattern for the file type. Next important thing that we should understand is the data representation when we talk about file set view. The data representation can be native, internal, or external 32. The native and internal data representations are implementation dependent, while the external 32 representation is common to all implementations of MPI that facilitate file interoperability. When we use the native data representation, then the data is stored in the file in the same way as it is in the memory. The advantage of this data representation is that we get data precision and I/O performance is not lost in type conversions. However, there is a disadvantage of this mode, and that is there's a loss of transparent interoperability within a heterogeneous MPI environment. The data representation, which is internal, can be used for I/O operations in a homogeneous or heterogeneous MPI environments. The MPI implementation, like I said, is free to use how it implements the internal data representation. It might as well be implementing internal in the external 32 format. So our external 32 format is the universal format that is suggested for interoperability. And please note that your MPI implementation could be supporting user-defined representations as well. So please check the manual of your MPI library. Here on this slide, we revisit the previous example of writing data to a file, with the difference that we would be using MPI file set view and MPI file write calls instead of MPI file write at call that we used previously. So let me go directly to the lines of code that demonstrate the usage of MPI file set view and file write. So here at line number 18, we see the call to MPI file set view. It accepts the file handle, the offset, the E-type, the file type, the data representation, and here we're selecting native data representation, and the MPI info object we're passing here is Basically, we're passing MPI info null. We're not setting any specific information or hints here. And then we have a call to MPI file write, and basically we close the file. In order to compile the code, we are using the MPI cc command here as shown on the slide. And please note that this code is available in my GitHub repository that is associated with the Better Scientific Software Fellowship. And here, after we compile the code, we run the code with 4 MPI processes using MPI run command. Depending upon the HPC system you're on, this command could be different. If you're working on a system that supports MPI exec, you might be using MPI exec here or MPI exec Hydra. Here I'm using MPI run. So after we run this code, basically what we will get is a file. The file name was data file3. That's the file we wrote. And note that this file would be a binary file. If we want to inspect the contents of this file, we can take a hex dump or an octal dump of the file with appropriate formatting options. So here on the slide, I showed how I'm using hex dump command to display the contents of the file named data file3, which is a binary file. And we would see this pattern of numbers printed here. And basically, this confirms that the data that was read from the buffer got written to the file correctly. There could be occasions when you want only one process to have access to a file at a time. And in such situations, you can use the MPI file set atomicity call. When you are enabling the atomicity mode, then the MPI IO will guarantee sequential consistency. And note that this can result in a significant drop in performance. And also note that this is a collective function call. MPI supports collective IO calls as well. Collective IO is a critical optimization strategy for reading from and writing to the parallel file systems. The MPI implementation optimizes the read and write requests based on the combined requests of all processes, and it can merge the request of different processes for efficiently servicing the IO requests, and hence basically improving the performance of the IO. Now, this is particularly effective, as in collective IO is particularly effective when the accesses of different processes involved in the communication are non-contiguous. MPI supports both blocking collective IO function calls and non-blocking collective IO function calls. Here on the slide, we have some of the examples of blocking collective IO function calls for reading and writing data in parallel. So we have MPI file read all, MPI file write all, MPI file read at all, and MPI file write at all. So all these calls end with underscore all. The calls here that have underscore at in them are the ones that use explicit byte offsets, and other calls which do not have underscore at in them are going to be using individual file pointers. It should be noted that the blocking collective IO functions for reading and writing have their signatures similar to their non-blocking counterparts. So the only difference that we would see in the signatures is in the name of the call itself. So non-blocking calls will have I included in them, as in here we have MPI file I read at all, and its blocking counterpart will have MPI file read at all. But rest of the parameters that this function uses, like I said, they are similar for both blocking and the non-blocking function calls. So these non-blocking collective functions can be useful for overlapping computations with I/O, and this is another critical strategy for improving the performance of the code. And these are defined for data access routines with explicit offsets and individual file pointers only. And these are not defined for shared file pointers. Anyways, we're not covering shared file pointers in this tutorial, but I just wanted to mention this as a side note. And please note that when we are using the non-blocking collective function calls, we should remember to call MPI wait function at appropriate places for synchronization and for guaranteeing that we get accurate results. Now let's look at an example to demonstrate the usage of collective non-blocking I/O calls. In this example, we will be using MPI file I write all and MPI file I read all calls. Now let us inspect this code line by line. The first few lines of this code are for including the standard header library files and mpi.h. Then we define size all in caps and set it to 64. In the main function, we define the file handle, which is fh. We initialize the MPI environment with MPI init. Then we have calls to MPI comrank and comsize. And here notice that this size is accepting size in lowercase basically. And then we have two buffers of length 64 defined and of type integer. And then what we're doing is we're initializing the buffer and we're calculating the offset values that tells us how much of the file would each process be responsible for writing. And then we open the file with MPI file open call, and the file we're opening here is testing async.out, and we're opening this file in the read and write mode. And notice that we are using the OR flag and we have MPI mode create passed here as well. So we are saying if the file does not already exist, then create it. And basically we would be using this for read and write purposes. Once we open the file, we call the MPI file set view function and we set the regions in the file for each process to work with. And if you notice in MPI file set view call, we're having the data representation as native. And then we are calling MPI file I write all for writing the buffer named buff. And then notice that we invoke MPI wait function call. So after we do the MPI wait function call, we close the file. Now that we have written the file and closed it, let's reopen the file and read the data into the buffer buff2. So here we are initializing buff2 to 0 with this for loop here. And then we open the file testing async3.out, the same one that we wrote to. And here we are opening the file again in the same mode. We are saying MPI mode create. And we're using the OR flag and saying MPI mode read and write. So here, then what we are doing is we are setting the view for each process to read the data from. And then we are having a call to MPI file I write all, and notice that we are reading the contents from the file into the buffer named buff2. And we specify the number of integers, or basically the number of values that should be read from the file by each process. And then we have a call to MPI wait and we close the file. Next, we are just printing the contents of the buffer to see what got printed or what got written inside the buffer. Next, we free the buffers and we call MPI finalize. The commands to compile the code and to run it are shown here on the slide. we're using MPI CC to compile the code and MPI run to run the code. And then we're taking the hex dump of the output file, which is testing async3.out, to inspect the contents of the file, and it looks as expected. When using MPI I/O calls, collective buffering can be used for coordinating the I/O at the application level, such that the total number of disk operations for I/O are reduced, and then the bottlenecks associated with thousands of processes writing to a shared file get mitigated. With collective buffering, a subset of the total number of processes participating in the job act as buffers over which the small data blocks are aggregated into larger data blocks, and then the aggregated data blocks are written to the disk or storage targets by the subset of the total number of processes. And hence this process reduces the total number of MPI processes participating in I/O at this stage, and then eventually this improves the I/O performance. We can pass MPI I/O hints to the MPI library and instruct or let it know that we are interested in using collective buffering or not. And then we can select also the number of processes that should be acting as aggregators, and we can set the optimal size for the buffers to use. We will talk more about MPI I/O hints on the next slide. Through MPI I/O hints, we provide extra information to MPI implementation for optimizing I/O. So hints are specified via info objects, and they let us provide information such as file access patterns and file system specifics that can enable optimization. Providing hints can enable an implementation to deliver increased I/O performance or to minimize the use of system resources. Please note that you can specify hints, but the implementation can choose to ignore them. Some MPI implementations support setting the environment variables for hints as well. And in general, though, you can have these three function calls shown on the slide for passing hints to MPI. You can use MPI file open, you can use MPI file set info, or you can use MPI file set view. We have already seen the usage of MPI file open and MPI file set view functions. In these functions, wherever we said MPI info null, in the place of that, we could actually pass the info object which contains actual hints. The hints could be in the form of, for example, striping factor or striping unit for Lustre. When we say striping factor, basically what we're saying is we are mentioning the number of OSTs across which the file should be striped. The striping unit controls the striping unit or striping size in bytes. The MPI file get info function can be used for getting the list of hints that are associated with the file. Please note that for these hints to work, an MPI library should be built with the Lustre support. For example, if it is MVAPage2 or OpenMPI, these implementations support the hints. The hints for collective buffering can also be passed through the similar mechanism like we discussed on the previous slide. Here on the slide, I'm showing the calls to MPI info set function, and this MPI info set function shows how to set striping factor, striping unit, the collective buffering nodes, and the MPI info, which is the first argument here, is basically the MPI info object that we declare, and we pass that here. And notice that these values that we provide, CB nodes, striping unit, and striping factor, which is the second argument, these are strings. So we have to specify them in double quotes. And then the actual variable or the actual values are the third argument or the third parameter to these function calls. Let's take a look at a sample code named providehints.c. This code is available in my GitHub repository for the Better Scientific Software Fellowship. And this demonstrates how to create an info object. So let's take a look at this code line by line. So the first few lines of the code are pretty much self-explanatory. So we are including the standard header file for IO. We are including MPI.h, and in the main function, we're initializing the MPI environment, having calls to MPI comRank and comSize functions. Then we are declaring a buffer named buff and initializing it to the loop index of the for loop. We're calculating offsets explicitly for each process. And then we're creating the MPI info object, myInfo. And then we are calling MPI info set and passing this myInfo object to it. And the hints that we're passing here with MPI info set are Lustre striping factor, and we're setting it to 4. And then we are setting the striping unit, and we're passing the value of 4 MB here. If you remember the Lustre examples that we covered in part 1 of the tutorial, there we used the Lustre command to explicitly set the stripe size and stripe count. And here we are using the MPI info set calls to do the same thing from within the code. Next, we open the file, and the file we're opening is data file striped22. And notice that we're passing MPI info object that we created, myInfo here, instead of MPI info null that we used in some of the previous examples. Then we basically use MPI file write at. We are using explicit offsets for positioning each process in the file for doing the writing task. And then we close the file, and then we free the info object. Then we call MPI finalize. Next, we will compile and run the code that we saw on the previous slide. After we run the code, we will get an output file named data file underscore stripe22 generated. We can inspect the stripe count and stripe size for this file by using the LFS getStripe command of Lustre. And as you would notice from the data presented on the slide, we were indeed successful at changing the default stripe count and stripe size for the files, because this new file that got generated has the stripe count of 4 and the stripe size is 4 MB. By default, the stripe count was 2. So this got changed here. Now let us consider a stenciled code involving an 8 by 8 array, such that the array can be broken down into 2 by 8 subarrays having ghost cells on top, bottom, left, right, thereby making the subarrays of size 4 by 10. And in this example, we would be considering the solution to 2D Poisson equation using Jacobi iterative method. And this code involves a 5-point stencil. The original code for this example is obtained from John Burkhart's website from the Florida State University. To elaborate further, after the solution has converged, each process should write its subarray to a shared file without including the halo region. Halo region is the extra rows and columns that are created around our subarrays for facilitating the exchange of cells in stencil code. We will create a temporary array for copying the values from the required indices of the subarray with the halo region, and we will calculate the offset for each process for beginning its writing in the shared file. Then we will open a file, set the view of each process, and use non-blocking collective write calls. We will also write the contents of the file back to another array and print it to verify the results. Now let's look at the code snippet associated with the stencil code. The complete code is available in the file named poison2d.c, and this file is available in my GitHub repository associated with the Better Scientific Software Fellowship. In the first few lines of this code snippet, we can notice that we declare a buffer of size 2 by 8, and then in the nested for loops, we are iteratively copying the values from the buffer named u_new, which is our solution array, and it contains the halo region as well. So we are copying values from u_new to the buffer of size 2 by 8. So these nested for loops basically each have two loop variables. One set of loop variables are for iterating over u_new array, and the other set is for iterating over the buffer buff. Then we are computing the offsets, and here we are having offset is equal to my rank multiplied by 16 multiplied by size of double. So this will help us calculate the starting point of writing the values by each process in the file. And then we are opening the file in the read and write mode. We are setting the view for each process, and we are passing the calculated offset here. Then we are invoking MPI I write all function. Basically, we're doing non-blocking collective IO here. And like I was mentioning earlier, when we do collective non-blocking IO, it's important that we do some kind of synchronization with MPI_wait function call. And then we close the file after this set of operations. In these snippets or lines of code on the slide, we're declaring another array called buff2, and we would be reopening the file for reading now. The same file that we wrote to, we would reopen that for reading, and we will copy the values from the file into this buffer and print the buffer. So the whole goal of this reopening of the file is to inspect whether the data got written correctly to the file. So we could have also used the hexdump call or the hexdump command on the Linux command prompt. However, here I'm just demonstrating a different way or a different technique of inspecting the contents of the file by reopening it and copying data from portions of it into a buffer and then printing the buffer. So here basically you notice that initially the buffer buff2 is initialized to 0, and then I open the file, and then I set the view for each process, and I invoke MPI I read all function. And then again, this function I read all actually is opening the file and copying its content to the buffer named buffer2. So notice that we're copying only 16 elements for each MPI process that's participating in the computation. And then we have call to MPI_wait, and then we close the file, and what we are doing here with the for loop printed at the bottom of the slide in this region. So we are printing the values of the buffer just to verify the correctness of the code. I was mentioning, we could also use the hexdump command to inspect the contents of the binary file named poison_out.out written by poison2d.c code. This we conclude part 2 of the optimizing IO tutorial, and thank you for your patient listening.